So the most common Riemann sum that we use, and this is kind of our base for everything that we're going to be doing when we want to estimate these areas between a function and the x-axis, is what's called the rectangular approximation method, or RAM for short. Um, when AP says Riemann sum, this is what they are talking about. They are specifically talking about RAM. So we have control over the width of the rectangles. It's nice to have the same width for every rectangle. So like, especially when we're working graphically, we work really hard to make sure there's the same width, but it's not a necessity. I have a later video where I have an example of, hey, if we're given a table of information, what if the widths aren't the same in that table? The height of our rectangles is going to be determined by the function, and we have three types of RAM to help us be consistent with how we're figuring out the height of each of our rectangles. So left RAM is where the height goes from the left side of the rectangle space up until we hit the function. Midpoint RAM from the midpoint of the rectangle space up until we hit the function, and right RAM from the right side of the rectangle space up until we hit the function. And this will make more sense as we do examples here. So, excuse me. I have here the function x squared, and I want to estimate the area under the curve on the interval 1 to 3. So I am looking at going from 1 here to 3 here. And what I want is this whole area. Now, that's not a nice shape for me, so I'm not going to be able to find it perfectly. So instead of finding it perfectly, we're going to estimate it. And if you notice, the problem itself says estimate. So we're even being told use 4 rectangles of equal width. You will also see the phrase 4 partitions. When it says 4 partitions, that means whatever shape we're using, we want 4 of them, and we want them to be equal width if possible. Since we're controlling this, I can make them equal width. So I'm going to be going every half unit in x. So I've got a rectangle that's going from 1 to 1.5. I've got a rectangle going from 1.5 to 2, from 2 to 2.5, and from 2.5 to 3. Now, to determine the heights, they're not telling me yet which way to use. On the AP exam, they will tell you which method they want you to use, left, midpoint, or right. I'm going to use left for this case, so we're going to be doing left RAM. So if I start at the rectangle between 1 and 1.5, the left RAM says use the left end of its base, so the 1, go up until I hit the function, and there's the height of my rectangle. So this rectangle has a height of 1 squared, because my function is x squared. So this is 1 squared, which is 1 tall. If I go from 1.5 to 2, I use the left end of its base, so the 1.5. I go up until I hit my function, and that's the top of my rectangle. Well, its height is the 1.5 until I hit the function, which is 1.5 squared, which is 2.25. Between 2 and 2.5, I use the left side 2 to go up until I hit the curve, which is at 2 squared, which is 4. There's the top of my rectangle. And then for the 2.5 up, that's 2.5 squared, which is 6.25. And those are my 4 rectangles. Well, I then need the area of each of them. Well, for my first rectangle, it has a width of 0.5, a height of 1. The second rectangle, width of 0.5, a height of 2.25. For the third rectangle, a width of 0.5, a height of 4. And for my third rectangle, a width of 0.5 and a height of 6.25. So I found the area of each of my 4 rectangles, and I add those up. And when I do that, I get 6.75. And there is an estimate for the area under the curve from 1 to 3 between x squared and the x-axis. if I were to do the same problem with RRAM, so I would still be going from 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3 for each of my rectangles. But now for RRAM, uses the right side of my rectangle. So for my first rectangle, I'd use the 1.5, go up until I hit the curve. And there's the top of my rectangle. For the 1.5 to 2, I'd use the right side, the 2, up until I hit the curve. And there's the height of my rectangle. For 2 to 2.5, use the right side of the rectangle, 2.5, up until I hit the curve. And then for 2.5 to 3, use the right side of the rectangle, up until I hit the curve. So now when I'm finding my first rectangle between 1 and 1.5, the width is 0.5. The height is 1.5 squared, which is 2.25. For my second rectangle, the width is 0.5. The height is 2 squared, which is 4. For the third rectangle, the width is 0.5. The height is 2.5 squared, which is 6.25. And for my fourth rectangle, the width is 0.5, and the height is 3 squared, which is 9. And when I go ahead and multiply all of that and add it together, I get 10.75. So with this, LRAM, if I go back and look at my work here, all of my rectangles were underneath the function. I didn't cover all of the area. And so I can see, because the rectangles are underneath the function, this is an underestimate. But when I look at RRAM, all of my rectangles are over the function. I have too much area. And so the 10.75 is an overestimate. And what this allows me to now say is, while I know these are estimates, I know the exact area is going to be something that's between the 6.75 that was the underestimate with LRAM and 10.75, which was my overestimate with RRAM. I'd like you to give it on example 4 in our notes. I want you to go ahead and do the same thing, but this time use midpoint RAM. It's going to take you a little bit longer because the math is not quite as friendly with the numbers involved. But go ahead and find midpoint RAM on the exact same function, same partitions, all of that.